Hi, this is Mrs. LaBarbara. This is Physics Chapter 10, Waves Intro, Video 6. Today's topic is speed of waves. The objectives are: understand speed of a wave is determined by medium only. Be able to calculate the speed, wavelength, frequency, and or period of a wave. Wave velocity is a vector quantity, so remember velocity has a direction. So to find the speed, speed equals the distance over time. That's the first equation we learned in this regions class. The distance for one cycle is the wavelength. The time for one cycle is the period. So V equals wavelength divided by period. 1 over period is the frequency. So wave speed equals to frequency times wavelength. That is the wave equation. Variables affecting wave speed. The speed of wave is not dependent upon properties of the wave itself, such as frequency, period, amplitude, or wavelength. Rather, the speed of the wave is dependent upon the properties of the medium and the medium only. So only alterations in the properties of the medium will cause a change in the speed. For example, in the class, everybody talks in the same medium, which is the air. So everybody's sound travel with the same speed. It doesn't matter what kind of sound you have. Here is an animation showing two waves, have different amplitude, different frequency, and different wavelength. But their speed is the same because they are traveling in the same medium. Speed is not frequency. Sometimes the two can be confused. Speed is how fast a wave is moving. Its unit is in meters per second. Frequency is how often a wave vibrates up and down. So a lot of times a wave can have a very high frequency, but have a smaller speed. This can be imagined as a child is working with an adult. Child little legs can move very, very fast, right? Have high frequency, but child speed can be slower than adult because adult has a bigger steps. So that's why even the child has high frequency, the child speed is smaller. So here is an animation of two kangaroos. They have a different frequency, but in this case, they have the same speed. So frequency and the speed are two different quantities. Okay, also another thing I want to talk about is higher frequency really result in a smaller wavelength. Let's talk about this example. What is the time required for the sound wave to travel from the tuning fork to point A? So in this case, we know the speed, we know the distance. So what is the time? So we use this equation V equals d over t to find t. Remember, t and v can be switched. So t equals d over v. 20 divided by 340, you have 0.059 seconds. Another example. A teacher attaches a slinky to the wall and begins introducing pulses with different amplitude. Which of the two poles below will travel from the hand to the wall in the least amount of time? In another word, which poles will travel fast? So let's talk about speed. What is speed determined by? Speed is determined by medium and medium only. Since two waves both travel in the same medium, the medium is slinky, so they must have the same speed. As a result, they must arrive at the wall in the same time. Another example, does the damping affect speed? Nothing affects speed except the medium. Damping is not changing the medium. Damping is change of amplitude. So damping does not affect speed. Example, round trip. So automatic focus camera is able to focus on objects by use of ultrasonic sound wave. The camera sends out sound waves that reflect off distant objects and return to camera. A sensor detects the time it takes for the waves to return and then determines the distance an object is from the camera. The camera lens then focuses at that distance. Now that's a smart camera. Suppose a sound wave has a speed of 340 meters per second, returns to the camera in 0.15 seconds after leaving the camera. Then how far away is the object? So here's a camera, here's the object. So basically, the question tells you the sound travels from the camera to the object and back in 0.15 seconds. So how far away, what is the distance? So V equals D over T, so D equals V times T. V is 340, it tells us. Now the time, you going there and coming back is 0.15. So just going there, you have to cut the time in half. So therefore, the time is 0.15 divided by 2, and you'll have 25.5 meters. That is the distance from the camera to the object. Another example, if the frequency of the sound wave increases, what happens to the wavelength? Let's see if the frequency increases. Let's talk about kangaroo. The top kangaroo frequency increased. As you can see, what happens to the wavelength? Wavelength becomes shorter because the wave speed is constant in this case. Another example, what is the wavelength of 2.5 kilohertz sound wave traveling at 326 meters per second through air? Kilohertz, this is prefix. Kilo is 10 to the 3. So let's see, V equals to frequency times wavelength. The wavelength equals to speed divided by frequency. So speed is 326 and frequency is 2.5 times 10 to the 3. So the answer is 0.13 meters. Another example, the diagram below represents a periodic wave traveling through a uniform medium. If the frequency is 2 hertz, what is the speed? So remember, if you know the frequency, you find the speed. Speed equals to frequency times wavelength, and wavelength is total length divided by number of cycles. The length, it tells us, not the total length, is 6 meters, but in 6 meters, what is the cycle? How many cycles is that? It's 1.5 cycle. So the wavelength is 4 meters. Then we can find the speed equals frequency times wavelength is 8 meters per second. Lastly, let's talk about the special waves. One is light wave, one is sound wave. The speed of light is 3 times 10 to the 8th meters per second, and that's in air or in vacuum. The speed of the sound, on the other hand, is much slower, which is 3.31 times 10 to the 2 meters per second. That's for standard temperature pressure. These two numbers are in your reference table on the first page. So basically now we're going to use these two constants to figure out either distance or time. Examples, what is the time required for the light to travel a distance of 1.5 times 10 to the 11 meters? By the way, 1.5 times 10 to the 11 meters, this is the distance from the sun to Earth. So V equals D over T. Solve for T again. We can switch these two variables. T equals D over V, which is 1.5 times 10 to the 11 meters divided by 3 times 10 to the 8th meters per second. So you'll have 500 seconds. So 500 seconds divided by 60, that's about how many minutes? So 8 minutes, about 8 minutes. So that's how long it's going to take the light traveling from the sun to Earth. Next one, a sound wave with a constant frequency of 250 hertz are traveling through air at STP. So right away at STP, the sound, we know the speed, it's in the reference table, 331 meters per second. What is the wavelength? So we use the wave equation. We can find wavelength equals V over F, and that gives us 1.32 meters. That's it for today. Thanks for watching. See you next time.